So we're going to do another example of curve sketching, this time with the logarithmic function. When you're dealing with these logarithmic functions, you got to be really careful. I want you to think back to our identity. If I have ln c to the a, we're usually allowed to bring this a out in front, a ln c. Now in this example, you do want to be careful with the 2, because if I were to compare ln of x squared with 2 ln x, these are quite different functions, because this one has a domain of x cannot equal 0, because you're not allowed to have a negative inside and you can't have 0 inside, and x squared is always positive. But this one would have to be x greater than 0. So in an example like this, if you were to bring this 2 out front, like the rule allows us to do, you would need an absolute value on the x, otherwise you would be changing the question. So be very, very careful with this original function. Try not to modify it, but also think about what would have to be true. So let's go through and do our domain. Now we can't have 0 on the denominator, so x cannot equal 0 for the denominator. On the numerator, a ln of a function, so ln of something. In the argument, this something needs to be positive and greater than positive greater than 0 and not equal to 0. So again, here we want to think about x squared being greater than 0, which is always true, except when x is equal to 0, we want x not to be 0. So I square a positive number, I always get a positive. So my domain in this case is the set of all x such that x cannot equal 0. And other than that, x can be any real number. Okay, so there's my domain. Again, you want to be really, really careful with the domain, because if you get the domain wrong, your number line and other things will also be wrong and things will look really messy. Let's go through and do our intercepts. We want to think about where does the graph have an x-intercept. So the x-intercept, we're going to set y equal to 0 and solve for x. So I multiply both sides by x. So ln x squared equals 0. And again, at the start of the course, we used to practice these. We need to think about what function undoes the ln function. It's the e function. So I'm going to take the e on both sides. E and ln are inverse functions of one another. So x squared is equal to e to the 0, which is 1, which means x is equal to plus or minus 1. So my x-intercepts are 1, 0, negative 1, 0. My y-intercept of the function, I'm going to set x equal to 0, but that's not possible because I can't set x equal to 0 because x is not allowed to equal 0. So there's no y-intercept. So again, be careful, there's no y-intercept. So there is something weird happening at x equals 0. What do we think it is? Well, if I sub 0 into my function, I get something that's a problem divided by something that's a problem. So just kind of be aware of that as we look through this example. Let's summarize that information. So there's my x-intercepts, my y-intercept, there is none. Let's do our symmetry. So what we want to do when we're calculating symmetry is compute f of minus x. So we're going to get ln minus x squared over minus x. The negative value squared gives me just the positive value over negative x. You can notice in this specific example, this stuff is exactly f of x, and then there's a negative outside. So it's negative f of x, which means my function has odd symmetry. Whatever's happening on the left of my graph is also being kind of on the right, but there's sort of two reflections. The graph reflects in the x-axis and the y-axis, and that would be how there's a mirror image of the graph on one another. Now here, for my asymptotes, we want to think about what are vertical horizontal asymptotes. So y equals ln x squared over x. I feel like there's a vertical asymptote at x equals 0. Let's actually go, I'm going to put a question mark here because I feel a little unsure about that, because ln of 0, I don't know what that is, but 0 on the bottom, I think, x equals 0 is a non-permissible value, which kind of makes me lead into thinking it's a vertical asymptote. Let's see if this actually is true or not. So we're going to approach limit as x approaches 0 from the right of ln x squared over x. So what I'm going to get is limit as x approaches 0 from the right. I'm going to kind of write this as ln of x squared times 1 over x. What is ln of 0 from the right? So I sub in a 0, I square it, I get 0. The ln function looks like this. So as x approaches 0, that's slightly positive. I'm just going to write it as ln of 0 plus divided by 1 over 0 plus. Ln of 0 plus is negative infinity because this graph is going down to negative infinity. And then 1 over 0 plus goes to positive infinity. So the overall result here is negative infinity. Because this goes to infinity or negative infinity, it does confirm that this is a vertical asymptote. We're going to take that away. We can summarize and say x equals 0 is a vertical asymptote. Let's do the limit as x approaches 0 from the left of ln x squared over x. I'm going to kind of break it up again. Sometimes these ln limits and e limits get kind of tricky, so be careful to look out for L'Hopital's rule. And again, we'll be doing a future lesson on it, but for right now, just kind of think, is it infinity over infinity, 0 over 0? Try to do the derivative of the top, derivative of the bottom. I sub in 0 from the left, I square it, I'm going to get a ln of 0 plus again, times 1 over 0 minus, which is minus infinity times minus infinity, which will give me a plus infinity. So it's confirming that x equals 0 is a vertical asymptote. Let's work through our horizontal asymptotes. Limit as x approaches infinity of ln x squared over x. Now this is one of those examples where we're going to think about L'Hopital's rule. I'm going to do it in a different color here so I don't confuse you. The limit as x approaches infinity of my numerator is ln of infinity, which is big number. This is going to a big number. The limit as x approaches infinity of x is also a big number. We're going to apply L'Hopital's rule. Okay, so now when I apply L'Hopital's rule, I do the derivative of the top, which is 1 over x squared, times the derivative of the inside, which is 2x. So that's chain rule. When I do the derivative of the bottom, I get a 1. And I'm going to try to evaluate this limit again. Limit as x approaches infinity of 2 over x. That's what that simplifies to. 2 over a large number goes to 0. So that's going to confirm that y equals 0 is a horizontal asymptote. When I do the limit as x approaches minus infinity of ln x squared over x, same thing is going to happen. I'm going to apply L'Hopital's rule, the same as above. I get infinity over infinity, and it doesn't matter if one of these is minus infinity and one of them is plus. The fact that they're both infinities of some sort kind of refers to the fact that you can use L'Hopital's rule. So it's the same process above. I do the derivative of the top, derivative of the bottom, so I get 1 over x squared times 2x, and the derivative of the bottom is 1. Now if I wanted to show you the process, limit as x approaches minus infinity of ln x squared is positive infinity. The limit as x approaches negative infinity of x is negative infinity. So like I was saying, it doesn't matter that one is positive and one is negative. It just matters that they're infinities of some sort. I simplify this function up 2 over x, and I also get 2 over a large number, or negative large number, which also goes to 0. So that confirms my horizontal and vertical asymptotes. So let's go in and we're going to start drawing a rough sketch of what we notice. I'm going to come back and erase that line. I'm going to kind of do a more central graph. So I have x-intercepts at 1 and minus 1. So there's positive 1. There's negative 1. I know that as x goes to infinity, the y's are both going to 0. So it's either going to go this way or this way. There's an asymptote here, and there's an asymptote here. So the graph has to go towards the asymptote in one of the two directions. I also know that there's odd symmetry happening on the graph. And I also know that x equals 0 is a vertical asymptote. Now when I draw my vertical asymptote in, I make the dotted line go all the way through that x equals 0 line or the y-axis, because the graph is definitely not allowed to cross these vertical asymptotes. They have to stay on the left or stay on the right. So that's what we have so far. Oh, and we also know that the limit as x approaches 0 from the right was negative infinity, and as x approaches 0 from the left, it's positive infinity. So this is going to come down, and this one is going to go up. So it's likely going to come down through that point somehow. Same thing on this function. It's going to go up and then come down through that point somehow. I just want to make sure that it looks like an asymptote. And you can see if I reflect either piece along the x and y-axis, they would land right on each other, which is kind of helping with the odd symmetry of the function. We'll do our first derivative stuff. So let's go ahead and take our first derivative of the function. Y is equal to ln of x squared over x. Let's go ahead and do our first derivative. This is going to be quotient rule. So f prime of x is derivative of the top is chain rule times the bottom minus, leave the top the same, the derivative of the bottom is a 1, all over the bottom squared. Let's clean up this function. X squared, those would all cancel out. So I'm left with f prime of x equals 2 minus ln of x squared over the bottom squared. I'm going to circle this response because that's important to know. That's what I'm going to sub my values into. I want to check where is the derivative equal to 0. This would mean that 2 minus ln of x squared has to equal 0. So I'm going to move the ln to the other side. Ln x squared equals 2. I need to undo the ln function by using the exponential. X squared equals e squared. X is equal to plus or minus root e squared, which is plus or minus e, which is approximately plus or minus 2.71. 828, and that's all I know. Okay, so that's where the derivative is 0. F prime of x is a does not exist when x is equal to 0, but we want to make a note that this was a vertical asymptote so we don't accidentally classify it as local maxes and mins because it's not in the domain of my function. So let's set up a number line. X is equal to 0 goes on there. Positive e, negative e, which are approximately 2.71. Vertical asymptote, and we're going to test the signs. So I'm going to go ahead and test the signs here. So I take my second derivative, I test the signs, so I'm testing the signs into this yellow function. Now you want to know that the ln of x graph looks something like this. So when I take a number like negative 3 and I sub it in, negative 3 squared is 9. Ln of 9 is way over here. This is 1, and 9 is way over here. So I'd assume that that value on the numerator is way bigger than 2. So 2 minus that number will be negative, and the numerator is always positive. I take a number like negative 1. I square it. Ln of 1 is 0. and then square the bottom. So this is a positive. And you keep going and do the values. You're going to get positive, negative. So what does that tell us about the original function? So again, when you're subbing them in, you need to be able to do this by hand and kind of think through the problem, okay? So what does this tell us about the original function? It tells us that the original function is decreasing, increasing, increasing, decreasing. So let's write our sentences down for what's happening. So f of x is increasing on the interval negative e to 0 union 0 to e, because that derivative is positive.
The North Bakken
F of x is decreasing
because I started at the top. So if you start
on
at Weird Hill and kind of
negative infinity to negative e union e to infinity, because f prime of x is less than 0. So those are part of my solution.
Under Southeast Saskatchewan.
We want to label the local maxes and local mins. So there's a local minimum
I'm
at
looking on the point.
negative e, because the sign is switching from negative to positive.
So just the last
And there's a local maximum at positive e and that y coordinate.
That I've got so far.
And because the sign, so this is because f prime changes from negative to positive, and this one is because f prime changes from positive to negative. So again, if we want these y coordinates, if we're solving for these y coordinates, we get ln of x squared over x, which would be ln of e squared. Ln of e cancel out, so it'd be 2 over e, or negative e in this case. And this one would be 2 over positive e when you sub it in. So be super careful when you're subbing those in. Make sure you get the right y coordinate there. So again, I can just show one example. Ln of e squared over e, and the ln and e cancel and you just get 2 over e. Those are also part of our solution. So let's go add that in. So at negative 2.71 we have a minimum, and at positive 2.71 we have a maximum. So let's put those into our graph. That's 1 when x is 2, x is 3. So when x is 2.71, we had a maximum. This is going to go up to the maximum and then back down towards the asymptote. So that clears up that. And on this side, we're going to have negative 2, negative 3. There's a minimum at negative 2.71 and whatever y coordinate that is, which I don't know right now. And that clears up that part of the function for us. So we know it has to be on the bottom. And that looks like a rough sketch of my graph. So now let's check. The function has to be decreasing, which is going down, which is true. Then it's going up, then it's going up, then it's going down. So that's true. My increasing, decreasing information matches up. So let's go ahead and do the concavity information and see if that supports the graph we've already drawn. It looks like it's probably going to, but let's go ahead and finish that up. So we need to solve the second derivative. Okay, so I'm going to write my first derivative down for us over here, which was 2 minus ln of x squared over x squared. So that's my first derivative. So let's go ahead and do the second derivative. So the derivative of the top, 1 over x squared times 2x, times the bottom. So now we're doing quotient rule, minus, I leave the top the same, times the derivative of the bottom, all over the bottom squared. You're going to notice that each of these terms has at least one x in it, so I'm going to cancel at least one x out of everything. So minus 2. Now I'm going to cancel out that x, and those x's are going to cancel out on their own. So I'm going to get a negative 2 minus, this x is going to cancel out, so I'm going to get minus 2 times 2 minus ln x squared. Divided by, I divide out one of the x's, I get x cubed. Now I'm going to expand minus 2 minus 4 plus 2 ln x squared all over my bottom cubed. So I'm getting minus 6 plus 2 ln x squared over x cubed. And that's sort of my simplified second derivative. I'm going to also factor out a 2, and I'm going to get ln x squared minus 3 all over x cubed, and this is my simplified second derivative. So now that's an important thing. I'm going to highlight it. That's the solution to my problem. Well, that's my derivative. Where does the derivative equal 0? Second derivative equals 0. So that would mean that ln of x squared minus 3 would have to equal 0. Ln of x squared equals 3, e on both sides, so 2 will equal e to the 3. Sorry, my apologies. X squared will equal e to the 3. X is going to equal plus or minus e to the 3, but square rooted. So where does y double prime, where is it undefined or does not exist? It's when x is equal to 0. Again, I'm going to label that as a vertical asymptote. That point cannot get classified as inflection points, maxes, mins, or anything like that. So 0, e cubed, and then cube rooted, negative root e cubed and cube rooted. And we're going to test the signs in my second derivative. So be very careful that you can evaluate this by hand. Use a calculator if you need, but try to evaluate it by hand. What you should get when you work out the signs is negative, positive, negative, positive. So what does this tell me about the original function? Concave down, concave up, concave down, concave up. Let's summarize. The second derivative is positive, so therefore the original function is concave up on the interval negative root e cubed to 0 union positive root e cubed to infinity. F of x is concave down on negative infinity to negative root e cubed union 0 to root e cubed. So we know that concave up is when the second derivative is positive, concave down is when the second derivative is negative. Those are part of my solution. Is there any sign switches? There's negative to positive, positive to negative, negative to positive. But again, this is a vertical asymptote, so I can't classify it. So I'm just going to write inflection points at x equals plus or minus root e cubed. And then if I wanted the y coordinate, we could just write it like this for now. F of root e cubed, negative root e cubed, f of negative root e cubed. It's kind of irrelevant to my graph unless I really start to watch the accuracy on the y-axis. So let's go ahead. The x is more important to know. So that's plus or minus. E is approximately 2. So you're doing, 2.71. So you're doing about 3 cubed, which is 27, and then square rooting 27, which square root of 25 is 5. So let's just say approximately around the 5-ish mark. But again, you would have to use a calculator just to get the accuracy on that. So plus or minus root 5 or 5 approximately. So what we can say is in green, the inflection point, I don't know, I'll label it there, inflection point. It's going to be at root of e cubed and then f of root e cubed. This point was my maximum, which was at e, f of e. This point was my x-intercept, other x-intercept. Negative e, f of e was the minimum. And then the other inflection point is somewhere on this side symmetrical. So negative root e cubed and f of root e cubed. And you can see that if I were to reflect this graph on the x-axis and then the y-axis, these graphs would be identical, which is helping with the odd symmetry. And that's that example.